last lecture we discussed Gauss theorem and we stopped at that surface integral over a closed surfaces between electric field intensity and area ds is equal to q upon epsilon naught. This thing we proved in our last lecture. Today we will be making use of this theorem or Gauss law to find the electric field due to a thin positive charge sheet, and secondly electric field due to a solid charged sphere. Then we will discuss capacity of a conductor and of various types of capacitors like parallel plate capacitor, spherical capacitor and cylindrical capacitor. So discussing the first topic, electric field due to a thin positive charge sheet. This we will discuss on slides. इलेवन करो शुरू. So today's topic is application of Gauss law और Gauss theorem. Gauss theorem जो हमने प्रूव की थी उसमें मैंने आपको बताया था, it states that the surface integral over a closed surface between electric field intensity and area is equal to 1 upon epsilon naught times the charge enclosed. This is Gauss theorem. So we are applying this law for finding the electric field due to an infinite thin plane sheet of positive charge having a uniform charge density sigma on both sides of the sheet. So this is your sheet of positive charge. Consider an infinite thin plane sheet of positive charge having a uniform charge density sigma on both sides of the sheet. By symmetry, it follows that electric field is perpendicular to the plane sheet of charge and is directed in outward direction like this. To find electric field due to plane sheet of charge at any point P, P is this point, any point distant r from it, choose a cylinder of area of cross section S through the point P as the Gaussian surface, this one, this cylinder. Since electric field of the plane sheet of charge passes only through the two circular caps of the cylinder like this one and this one. If E is the magnitude of electric field at point P, then electric flux crossing through the Gaussian surface, this one, is given by integral E dot ds, and it is equal to integral surface S1 EDS plus integral of surface S2 E dot ds. Now this integral over a closed surface S1 EDS is equal to ES, and integral over a closed surface S2 EDS is equal to again ES, same. So it will be equal to 2ES, because when you solve this it will be EDS cos theta, and here theta is 0 degree, so cos 0 is equal to 1, so it will be ES, and this will be again ES. So integral E dot ds for this will be equal to 2ES, ES plus ES. Charge enclosed inside the Gaussian surface. Charge enclosed is a Gaussian surface लिया हमने cylindrical, that is Q will be equal to sigma into surface area S, where sigma is surface charge density. So from Gauss law, integral over a closed surface S EDS will be equal to Q upon epsilon naught. So comparing these two equations, कौन सी, equation number 1 and equation number 3, we get 2ES is equal to sigma into S upon epsilon naught, or electric field intensity E is equal to sigma upon 2 epsilon naught, where sigma is the uniform charge density, surface charge density, which shows that magnitude of the electric field is independent of the distance from the sheet. जो हमारा फाइनल एक्सप्रेशन आया इलेक्ट्रिक फील्ड एट पॉइंट P ड्यू टू दिस थिन प्लेन शीट ऑफ पॉजिटिव चार्ज इज इक्वल टू sigma upon 2 times epsilon naught, where epsilon naught is the permittivity of the free space. So this E is electric field density is independent of the distance of the point P from the thin sheet of positive charge. In case the sheet is negatively charged, the expression will remain same, but the direction will change. In that case, E will points normally towards the sheet. जो positive charge था उसमें it is away from the positive sheet. Here it is normally towards the sheet, and surface charge density sigma is equal to total charge upon surface area having units coulomb per meter square. So this is the formula for the electric field intensity due to an infinite thin sheet of positive charge. Then second is electric field due to a solid charged sphere. This is your solid charged sphere, this one having radius r, and here P is a point where we want to find the electric field intensity due to this solid charged sphere. So there are three possibilities. First possibility is when the point P lies outside the sphere of charge. Second is when the point P lies on the sphere of charge, and third possibility is when the point P lies within the sphere of charge. So we will discuss each case one by one. Case 1, when the point P lies outside the charged sphere. Draw the Gaussian surface to the point P so as to enclose the sphere of charge. In this case, the Gaussian surface is a surface of radius OP equal to r. This radius OP, this one, small r, and center O. This is the center, concentric. Let E be the electric field at point P. Here this is any point P which is lying outside the sphere of charge, and electric field at that point P is E due to the sphere of charge plus Q. It is clear that field due to the sphere charge is spherically symmetrical. That is, at every point on the surface of the sphere, the field has same magnitude and is along normal to the surface. This is your Gaussian surface, this one of radius small r. So magnitude, so the field has same magnitude and is along normal to the surface. So total electric flux to the Gaussian surface is given by, जो हमारा गॉस लॉ के हिसाब से, इंटीग्रल E dot ds is equal to integral over surface S E dot ds, or it is equal to integral over a closed surface E ds, which is equal to, this is E ds cos theta, theta is 0 degree, cos is equal to 1, so it will be equal to surface area of the sphere, which is equal to 4 pi r square. So it will be equal to E into 4 pi r square, where E is electric field intensity and this 4 pi r square integral of ds is the surface area of the sphere of Gaussian surface having radius small r. So from Gauss theorem, this E into 4 pi r square is equal to Q upon epsilon naught, or electric field E will be equal to Q upon 4 pi epsilon naught into r square. Just यहाँ से E will be equal to Q upon 4 pi epsilon naught into r square. This is the case when the point P lies outside the sphere of charge, which is same as that of a point at a distance r from the charge q. तो ये फार्मूला जो है बिल्कुल वैसे ही है जैसा कि ये किसी भी पॉइंट पर जो डिस्टेंस r पर है किसी चार्ज से, उसकी वैल्यू यही होती है, E इज इक्वल टू क्यू अपॉन 4 पाई epsilon naught into r square. It shows that for a point outside the sphere of charge, the sphere behaves as if all the charge on the sphere were concentrated at its center. So sphere behaves as a point charge. If rho is the uniform volume charge density of the sphere, then this charge q will be equal to 4 by 3 pi capital R cube into rho. This capital R is the radius of the sphere of charge. So this charge q will be equal to 4 by 3 pi R cube volume of the sphere into volume charge density sigma. Putting the value of this q in equation 1, we get E is equal to 4 by 3 pi capital R cube into rho over 4 pi epsilon naught into r square. ये जो हमारी पहली इक्वेशन थी, इसमें हमने just we put the value of q here. So the value of E will come out to be rho capital R cube over 3 epsilon naught into r square. So electric field intensity at point P due to a solid charge sphere when point P lies outside the sphere of charge is equal to rho r cube upon 3 epsilon naught into small r square. This is the case when r is greater than r. R is the radius of the Gaussian surface and capital R is the radius of the sphere of charge. Case 2. In the second case, when the point P lies on the surface of the sphere charge, in this case, the area of the Gaussian surface is equal to the surface area of the sphere charge and it is equal to 4 pi capital R square. R is equal to capital R. So putting R into capital R in equation 3, we get कौन सी equation? इस equation में अगर R is equal to capital R put कर देंगे, उस केस में the value of electric field intensity when the point P lies on the sphere of charge is equal to rho r upon 3 epsilon naught. Okay. On case 3, when the point P lies inside the charge sphere, तो ये जो बड़े वाला स्फीयर देख रहे हो जिसका रेडियस कैपिटल R है, ये स्फीयर ऑफ चार्ज है और इसके अंदर हमने पॉइंट P लिया है जो कि एट ए डिस्टेंस R है सेंटर ऑफ द स्फीयर ऑफ चार्ज से. तो इस केस में जो आपकी गॉसियन सरफेस है वो ये वाली है, दिस वन. In this case, the Gaussian surface is spherical whose center is O and radius OP is equal to R. If Q dash is the charge enclosed by the Gaussian surface, then we have E into 4 pi R square. इसके लिए हम निकाल रहे हैं E into 4 pi R square will be equal to Q dash upon epsilon नॉट. हमने यही गॉस लॉ अप्लाई किया इसके लिए जो पहले फॉर्मूला ड्राइव किया था ऊपर हमने शुरू में, जिसमें E इंटू 4 पाई E इंटू सरफेस एरिया इज इक्वल टू चार्ज एनक्लोज इंटू 1 अपॉन एप्सिलॉन नॉट टाइम्स. सो E इंटू 4 पाई आर स्क्वायर इज इक्वल टू क्यू डैश. ये जो क्यू डैश क्या है, इसके चार्ज का कुछ हिस्सा, ये टोटल चार्ज क्यू है लेकिन इस पॉइंट पे कितना चार्ज इंक्लोज किया है उसको हमने क्यू डैश माना है. जब पॉइंट पी आपका इस स्फीयर ऑफ चार्ज के अंदर है. So E is equal to Q dash upon 4 pi epsilon naught into R square. So electric field intensity at point P when point P lies within the sphere of charge is equal to q dash upon 4 pi epsilon naught into r square. Now q dash will be equal to volume of the sphere into volume charge density. So volume charge density is q upon 4 by 3 pi r cube. This is your volume charge density into volume of the Gaussian surface, which is equal to 4 by 3 pi r cube. So q dash will be equal to q small r cube over r cube. इसको जब हम सिंप्लीफाई करेंगे, the value of q dash will come out to be q r cube upon capital R cube. So putting for q dash in equation 5, कौन सी equation? ये वाली. We get E is equal to q r upon 4 pi epsilon naught into r cube. Since q is equal to 4 by 3 pi r cube rho, E will be equal to q r upon 3 epsilon naught. इसको फिर से देखें एक बार इस केस को. ये हमारा पॉइंट P है और ये आपका स्फीयर ऑफ चार्ज है जिसका रेडियस r है. ये थर्ड केस है जब पॉइंट P इज लाइंग विद इन दी स्फीयर ऑफ चार्ज. तो ये हमने कोई पॉइंट P लिया यहाँ पे जो कि रेडियस r पे है और स्फीयर ऑफ चार्ज के अंदर है. जो आपका स्फीयर ऑफ चार्ज है उसका रेडियस r है और जो गॉसियन सरफेस हमने चूज किया थ्रू पॉइंट P उसका रेडियस जो है वो स्मॉल r है. ठीक है. तो इस केस में हमने गॉस लॉ अप्लाई किया. इसके लिए क्या होगा, गॉस लॉ की जो इक्वेशन बनेगी E इंटू 4 पाई आर स्क्वायर इज इक्वल टू, और अगर हम माने कि जो उसने चार्ज एनक्लोज किया है वो Q डैश है तो E into 4 pi r square will be equal to Q dash upon epsilon naught, where epsilon naught is the permittivity of the free space, or E will be equal to Q dash upon 4 pi epsilon naught into r square. Clear? अब इसके बाद हम निकालेंगे Q dash की वैल्यू कितनी है. तो Q dash की वैल्यू निकालने के लिए हमने क्या किया, ये है वॉल्यूम चार्ज डेंसिटी, दैट इज चार्ज अपॉन वॉल्यूम ऑफ द चार्ज स्फीयर, दैट इज योर वॉल्यूम चार्ज डेंसिटी. तो Q दिस विल बी इक्वल टू Q अपॉन 4 by 3 पाई कैपिटल R क्यूब इंटू वॉल्यूम ऑफ द गॉसियन सरफेस स्फीयर, दैट इज इक्वल टू 4 by 3 पाई R क्यूब. Clear? Volume charge density into volume of the enclosed surface 4 by 3 pi r cube. तो यहां से जो हमें वैल्यू मिली Q डैश की, दैट इज इक्वल टू Q स्मॉल r क्यूब अपॉन कैपिटल R क्यूब. तो जे Q डैश की वैल्यू हम पिछली इक्वेशन में पुट कर देंगे तो यू विल गेट E इज इक्वल टू क्यू आर अपॉन 4 पाई एप्सिलॉन नॉट इंटू कैपिटल R क्यूब. अब जो Q की वैल्यू है, Q की वैल्यू क्या है, वॉल्यूम चार्ज डेंसिटी इंटू वॉल्यूम ऑफ द चार्ज स्फीयर. सो इट इज इक्वल टू 4 by 3 pi r cube into rho, volume charge density. So this equation becomes E is equal to rho r upon 3 epsilon naught. So these were the three cases for the electric field intensity due to a solid charge sphere when the point P lies outside the sphere of charge. Secondly, when the point P lies on the sphere of charge, and thirdly, when the point P lies inside the sphere of charge. Okay. So next topic is capacity of a conductor. Capacity of a conductor is defined as the ratio of charge to its potential. Ratio of charge to its potential. If Q is the charge on the conductor and V is the potential to which charge is raised, then capacity is equal to charge upon potential. So C is equal to Q upon V. If V is equal to 1 volt, then C is equal to Q. Therefore, capacity of a conductor is also defined as the amount of charge required to raise its potential by unity. The unit of capacity is farad. So as we know, C is equal to Q upon V. If Q is equal to 1 coulomb, V is equal to 1 volt, then C is said to be 1 farad. Capacity of a conductor is said to be 1 farad if 1 coulomb of charge raises its potential by 1 volt. Farad is a very big unit. Other small unit of capacity are microfarad, nanofarad and picofarad. 1 microfarad is equal to 10 to the power minus 6 farad, 1 nanofarad is equal to 10 to the power minus 9 farad and 1 picofarad is equal to 10 to the power minus 12 farad. So these are the smaller unit of capacity which are commonly used for defining the capacity of a capacitor. Capacitor. So what is capacitor? It is a device which has large capacity in small space and stores electricity. It is also called condenser. So it is a device which has large capacity in small space and stores electricity. There are various types of capacitors in use: parallel plate capacitor, spherical capacitor, cylindrical capacitor. So we will discuss one by one. First of all, parallel plate capacitor. So this is your parallel plate capacitor. Here X and Y are two conducting surfaces. The surface can be rectangular, circular or spherical, placed parallel to each other and separated by a medium. The plates are called coatings of the condenser and the medium separating them is called dielectric. Dielectrics are those materials which do not conduct electricity. They are called insulators or dielectrics. Those materials which do not conduct electricity are called insulators or dielectrics. They don't have free electrons for electrical conduction. The molecules of a dielectric can be polar or non-polar. One of the plate of condenser is connected to the source of charge and other is earthed so that electric field develops in the medium. So just see this figure. Here X and Y are two surfaces, charge, positive charge is given to surface X. Due to induction, the negative charge appear on the inner side of the plate Y and the outer plate Y is earth. So electric field intensity outside is 0. The only electric field intensity exists within this region, this one between X and Y, and this electric field intensity E is equal to sigma upon epsilon naught, and D is the distance between these two conducting plates X and Y. So suppose a parallel plate capacitor is formed by two parallel conducting plates X and Y, each of area A kept separate by a distance D. Suppose plate X has surface charge density plus sigma, then for plate Y it will be minus sigma. The electric field intensity in the region between the plates will be given by the relation E is equal to sigma upon epsilon naught directed downwards, while it will be 0 in the region outside the plates. So, only E will be only existing in this region. Outside this plate and outside this plate it will be 0. If V is the potential difference between the plates, then this potential difference B will be equal to E into D. E is the electrical intensity and D is the distance between the two plates. So, it will be equal to sigma D upon epsilon naught, where epsilon naught is the permittivity of the free space. The total charge on each plate is Q and it is equal to area of the plate into surface charge density sigma, A sigma. If C is the capacity of the conductor or capacitor, then C is equal to charge upon potential. So, C is equal to Q upon V, or it is equal to A sigma upon sigma D upon epsilon naught, or it will be equal to A epsilon naught upon D. Sigma will cancels out. So, capacity of the parallel plate capacitor will be equal to epsilon naught A upon D, where epsilon naught is the permittivity of the free space, A is the area of the plate and D is the distance between the two plates. If the plates are separated by a medium of dielectric constant K, then C will be equal to epsilon A upon D, where epsilon is the absolute permittivity, or it is equal to K times the epsilon naught, where K is dielectric constant. Hence, the capacity of a capacitor C according to expression show that it depends upon, it directly proportional to the dielectric constant, directly proportional to the area of the plates and inversely proportional to the distance between the two plates. Or you can say, with the introduction of the dielectrics, the capacity increases. With the increase in the area of the surface, the capacity increases, and with the decrease in the distance between the two plates, the capacity decreases. In series units, the capacity C is equal to K A upon 4 pi D, where capital K is equal to K times epsilon naught. Here small k is the dielectric constant. Okay. In this way, we find the capacity of a parallel plate capacitor whose outside or second plate is earthed. C is equal to epsilon A upon D. Clear? So, this is the capacity of a parallel plate capacitor. Next topic is capacity of a spherical capacitor. So, this is your spherical capacitor, this one. It consists of two concentric surfaces A and B. Positive charge is given to the inner surface of the spherical capacitor and outer surface is earthed, and due to induction the negative charge appear on the inner side of the sphere B, whereas the positive charge appear on the outside surface goes to the earth. So, the same way, first of all we will find the C will be equal to Q upon V, we will find the value of potential due to sphere A and potential due to sphere B, then total potential will be equal to V1 plus V2, then if V is the total potential, then C will be equal to Q upon V. So, this using this formula we will find the capacity of the spherical capacitor. So, coming back to the figure again, a spherical capacitor consists of two concentric spheres A and B of radii R1 and R2. R1 is the radius of the inner sphere and R2 is the radius of the outer spherical surface. The outer sphere may be hollow or it can be solid, whereas the inner sphere, the outer sphere is hollow, whereas the inner sphere may or may not be hollow. जो आपका बाहर वाला स्फीयर है ये खाली होगा, लेकिन जो अंदर वाला स्फीयर है it may be hollow or may not be hollow. The outer sphere is earthed from outside as shown. When a charge plus Q is given to inner sphere A, it comes on its outer surface. Charge minus Q is induced on inner surface of B, whereas positive charge induced on the outer surface of B flows to the earth, क्योंकि इसको हमने अर्थ किया हुआ है. Now, potential of sphere A due to its own charge, it will be equal to, say it is V1, V1 is equal to Q upon 4 pi epsilon naught into R1. Similarly, potential of sphere A due to charge minus Q induced on the inner side of the sphere B, इसके कारण जो potential होगा A के ऊपर B2 will be equal to minus Q upon 4 pi epsilon naught into R2. Therefore, total potential of sphere A will be equal to V1 plus V2 and it will be equal to Q upon 4 pi epsilon naught taking outside common into 1 upon R1 minus 1 upon R2 because it is having minus sign. Since the sphere B is earthed, therefore its potential is 0. तो जो B हमारा sphere है, क्योंकि इसको अर्थ किया हुआ है, इसका potential जो होगा वो 0 होगा. So potential difference between these two spheres A and B will be equal to total potential of sphere A minus total potential of sphere B, that is V minus 0, it will be equal to V. So potential difference between the two spheres of the capacitor is Q upon 4 pi epsilon naught into 1 upon R1 minus 1 upon R2, or it is equal to Q upon 4 pi epsilon naught into R2 minus R1 over R1 R2. If C is the capacity of the capacitor, then we know that C is equal to Q upon V. Therefore, capacity of spherical capacitor will be equal to 4 pi epsilon naught R1 R2 upon R2 minus R1 when outer surface is earthed. In SI units, the capacity will be in farads. Now, third is capacity of a cylindrical capacitor. This is your cylindrical capacitor you are seeing here, this one. It consists of two concentric cylindrical shells. The space between the two cylinders contain air. ये आपकी एक शेल है ये वाला, जिसका रेडियस आपका आर ए है और ये आउटर जो सिलेंडर है उसका रेडियस जो है वो आर बी है और ये इसका एक्सिस है दिस वन. जिसके along this distance is RA and this distance is RB. Suppose A and B are two sections of concentric coaxial cylinders of radii RA and RB, where RB is greater than RA. Suppose the cylinder B is earthed and charge lambda per unit length is given to the cylinder A. Consider a point P, this point P, this one, within the distance RB and RA. The point P is lying here. So, there are three possibilities. What are those possibilities? The potential electric field, the electric field at point P is given by, this will be 0 when the point P lies at a distance less than the radius of the inner cylinder. When R is less than RA, the value of electric field intensity E here is 0, and it is equal to lambda by 2 pi epsilon naught into R when the point P lies at a distance greater than RA but less than RB, that is here, somewhere here. This is this point P when it is at a distance greater than RA but less than RB, then the value of E at that point is equal to lambda upon 2 pi epsilon naught into R, and it will be again 0 when this point P lies outside the outer cylinder. So, electric field intensity is only existing when the point P is lying between the outer cylinder and away from the inner cylinder. That is, RA is less than R, less than RB. R is greater than RA and R is less than RB, where RA and RB are the radii of the inner cylinder and the outer cylinder, of which the capacitor is made of. This electric field is directed radially outwards at every point. If V is the potential difference between the two cylinders, then this V is equal to VA minus BB, that is potential due to the inner cylinder VA and potential due to the outer cylinder BB. So, it will be equal to integral between limits radius RA to RB ER dr, or it is equal to integral between limits RA to RB. Just put the value of this ER is equal to lambda by 2 pi epsilon naught into dr upon R. On solving this, lambda by 2 pi epsilon naught is constant, taking it outside, it is equal to integral between limits RA to RB dr upon R, and this is equal to lambda by 2 pi epsilon naught into log of R to the base E between limits RA to RB. If L is the length of the cylinder, this one, if L is the length of the cylinder, then total charge on the cylinder Q will be equal to lambda into L. Lambda is the volume charge density, Q is equal to lambda into L, where L is the length of the cylinder. If C is the capacity of the capacitor, then C will be equal to Q upon V, or just put the value of Q here, C is equal to lambda L upon lambda by 2 pi epsilon naught into log of RB upon RA to the base E. So, it will be equal to 2 pi epsilon naught L upon log of RB upon RA to the base E. Just converting it to the natural log to the base 10, then this C by L will be equal to 2 pi epsilon naught upon 2.303 log to the base 10 RB upon RA. When we say log to the base 10, it is already understood. When you don't write anything here, it means it is a log 10 base. So C by L capacitance per unit length is equal to 2 pi epsilon naught over 2.303 log RB upon RA. Therefore, capacity of a cylindrical capacitor C is equal to 2 pi epsilon naught L over 2.303 log of RB upon RA when medium between the cylindrical plate is air. So here epsilon is equal to 1. If there is a dielectric constant, dielectric medium is having dielectric constant value K, in that case this C by L will be equal to 2 pi K times epsilon naught upon 2.303 log RB upon RA, where RB is the radius of the outer cylinder and RA is the radius of the inner cylinder, this one. This is your RA and this is your RB. So in this way you can find the capacity of a cylindrical capacitor. So what we did, this is your cylindrical capacitor, this is inner concentric cylinder and this is outer concentric cylinder. The radius of outer concentric cylinder is RB and inner is RA, and then we have taken a point P which is at a distance which is greater than RA but less than RB, and then we find the value of electric field intensity at that point, and it comes out to be ER will be equal to lambda by 2 pi epsilon naught R, and within and outside the value of E is 0. We find the potential difference due to this, and then by using the formula C is equal to Q upon V, we found the capacity of a cylindrical capacitor. So this is all for today. Please note your DHA. Today you are given the following DHAs. Mark these DHAs as DHAs after CT1. पहला DHA आपका जो DHA 9 है वो क्या है? Using the Gauss theorem, obtain an expression for the electric field due to a solid charged sphere. Using the Gauss theorem, obtain an expression for the electric field due to a solid charged sphere. ऐसे second DHA आपका इसमें DHA 10 is explain the principle of condenser or capacitor, derive an expression for the capacity of a parallel plate capacitor. जो भी हम करके हटे हैं, 3 कैपेसिटर किया हमने, parallel plate capacitor, then spherical capacitor and lastly cylindrical capacitor. तो इस केस में आपने you have to find the capacity of a parallel plate capacitor. और जो लास्टली है तीसरा हमारा DHA है वो है derive an expression. DHA 11 is derive an expression for the capacity of a spherical capacitor. तो ये काम आपने आज ही कर लेना है, क्योंकि हो सकता है नेक्स्ट ट्यूसडे को आपको जो मैंने DHA दिए हैं वो सभी आपने सबमिट करने हैं अकॉर्डिंगली. तो इसलिए अपना काम पूरा रखें. अभी आप क्लासरूम में कुछ लिंक्स भेजे जाएंगे, जैसे आपने हर एक क्लास वाइज इलेक्ट्रॉनिक्स, इलेक्ट्रिकल जितने भी हमारी ब्रांचेस हैं इंडिविजुअली, तो आपको उसमें एनरोल करना होगा और जो भी काम आपको मिलेगा आगे से आपके बैच को आपको वो नोटिफाई किया जाएगा. for future, maybe after Tuesday, you will get all information regarding your DHs and other events which will be taking place afterwards, like CAs and CT2 syllabus or other test if taken anyone, that will be notified to you well in time. तो अभी आपकी जो क्लासरूम बनेगा, आई विल सेंड यू द लिंक्स अकॉर्डिंगली. अप टू ट्यूसडे यू शुड वेट फॉर ट्यूसडे, एंड बाय दैट टाइम you must complete your all work of DHs, because you will be submitting these DHs very shortly. Okay. So this is all for today. Thank you.